Hi, today we'll discuss on the design of Spur case, and Spur case design is based on the Lewis equation. So the derivation of Lewis equation before going to the derivation of the Lewis equation. So first we'll see the content what I have sent to you. That is mechanical drives I have given, and difference between the gate drives and belt drives, and have given why do we need gate drives and the tractional forces. So discussion on some tractional forces for a gate point of view I have given, and types of gates, four types of gates I have given, and some description. And here the contact there is between the two gates. So there is a pressure line and a pressure angle, and there is a starting point of a contact and a leaving point. This is what the line of action. Angle made by the line of action and the common tangent will give the pressure angle. So that we will use for the calculation purpose right now. And I have given some terminology used in gates. So different terminologies here. The module and the pitch circle diameter is very crucial that we will discuss right now. And the pressure angle cases for different cases for gate point of view I have given, that is rack and pinion, and pinion and the internal gates. So how the pressure line and pressure angles will take in action, so that I have discussed here. And the force analysis. Here I have to discuss the force analysis, both the spur gear, helical gear, and the level gears also. Here the force analysis I have taken consider the angle, that is what we call the force will act along the pressure line up to the tip of the common point. And this force is resolved into two components, that is a radial component and a tangential component. And this radial component and tangential one is converted to, there is a tangential force on the tooth and the radial load on the tooth. So we consider the tangential load acting on the gear. So this tangential force is again calculated in terms of power equations. Wt is equal to 60,000 P by 2 pi n, and the P is in power in kilowatts, and D is gear diameter in mm, and n is the speed in revolutions per minute. Coming back to the derivation of Lewis equation, the Lewis equation is what we call beam strength for the gear tooth. So we assume that this particular tooth as a cantilever beam consisting of Wt is a cantilever force acting at the free end of the cantilever beam, and B is the width, and the section is considered as a triangular cross section. And if you proceed for bending stress equation, and we will get the equation sigma by bending stress is equal to tangential load by B into Y. B is the width of the face width of the gear, and Y is the Lewis form factor. So this Lewis form factor is given by T square by 6 L into pi m. So we can refer from the data handbook equation number 12.5b. So this is available in the data handbook. And dynamic forces. So what is the process of dynamic forces induced? That we will discuss shortly. And in conclusion of that is a derivation of Lewis equation. So permissible working stress to be learned. That is working stress sigma naught is equal to sigma naught into CV. So here CV is the velocity factors that is calculated for different speeds is given in this particular aspect. And the velocity factor, pitch line velocity is pi d dash n by 60 into 10 power 3. So pitch line velocity is calculated. So here d is again converted into in terms of module that I will discuss in the problems. And the design procedure, when you come up to the design procedure, the entire design procedure depends upon the Lewis strength equation. There is a Lewis equation, that is what a beam strength equation. Based on that beam strength equation, you will design the entire gear. So for gear to be rotated, there is a gear has to rotate as a rolling element, two rolling elements. The gear should have one of the important parameters, a common module. for pinion as well as gear must have the common module. So module must be the same for both gear and pinion. Otherwise, the mating is not possible in design of gears. Therefore, module has to be designed in the design process. So coming to the permissible working stresses, this is the sigma naught into CV that I already discussed in the previous section, and dynamic tooth load WD is equal to WT plus WI. That is a steady tooth load, that is a transmission of torque load, and the WI is the incremental load is calculated by using this equation. So equations are available in data handbook and proceed. And the static tooth load, that is a static tooth load consisting of this basic Lewis equation itself. So here we have sigma Vy into P is a basic equation. So sigma as permissible stress is converted as transformed into sigma naught into Cv, that is considering the velocity factor, and pi P is the pitch circle diameter of the gear or pinion. So that is given by pi into n, circle diameter. So this will be in the equation of module now, and the Lewis form strength factor, Lewis form factor is given for different in-value profiles of the gear profiles. So based on the gear profiles, that is a 14.5 degree in value, this is the equation. 20 degrees in value, this is the equation, and for 20 degrees stubborn, this is the equation. So these equations are available in your data handbook for calculation purpose of Y. And wear tooth load is another load carrying without premature wear. That is a maximum load that the gear teeth can carry without premature wear depends upon the radius of curvature of the tooth profile and on the elastic and surface fatigue limits of the material. The maximum limiting load for the satisfactory wear of the gear teeth is obtained by the following equations, that is WW is equal to dV/K. So here dV is the dP is the pitch circle diameter, D is the face width, and Q is the ratio factor, which in turn depends upon number of teeth on the gear and the pinion, and the K is the load stress factor. So this wear load has to be checked once you calculate the number of teeth on the pinion or the module of the gear. So coming to the design procedure I have made for you for the examination point of view. The procedure is same for helical gears and dual gears. So only 4 steps to be followed. The first step is going to be determination of tangential load using the power equation. So here you will get the equation Wt in terms of module itself, and the gear, the second step is design based on pinion or gear. Sometimes if the material of pinion and gear is made of same materials, we treat it as pinion is feature, and therefore the design will be based on the pinion. And if the gear is and the pinion is made of different materials, suppose the gear is made of steel and the pinion is made of some plastic material or some aluminium material. So since both the gear and pinion are made of different materials, so we need to calculate the Lewis strength factor sigma naught into Y. So whichever is the value is going to be lower for pinion or gear, so that will be considered as the weaker, and the design will be for weaker part. Coming back to the next step of design procedure is Lewis equation, that is Wt is equal to sigma Vy into P, that is in which we will transform into sigma naught Cv Vy pi into P. So here the caution is different textbooks they have formed in different calculation processes design. So we are following one particular procedure. So that is all the terms is converted into in terms of module. So let us see what are the terms will be converted into module. That is pitch line velocity V will be in terms of module. So that will comes in the velocity factor Cv. The velocity factor Cv, power transmission P, pitch circle diameter P, that is pi into m, and the face width B, here we will be assuming in terms K into m. So this k into m, that is 10 times or 20 times of module considered for base width. So the Lewis equation will be in the form of a cubic equation here. So this cubic equation will be solved from your calculators directly, and you can get the value of m. So sometimes some textbooks they will give trial and error method. So the best solution is about this is and once you calculate the module and the parameters of the gate, that is number of teeth and diameters and face width and everything, so we can check for wear loads. After calculating the wear load, we have to check this wear load should be greater than the tangential load for safe design. So here only simple 4 steps are available for the design of Spur gate. Similar procedure, similar steps can be followed in case of helical gates with minor modifications and bevel gates also. So problems will be solved shortly. So I'll stop here and let's see the problems to make a couple of notes after clarifying the outcomes.